Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, we're happy to have Girida Kumaran here to speak with us today. James Allen, PhD student from UMass, and I'll let him go ahead and give his talk.
Thank you, Dennis. Hello, good morning, and welcome to this talk on efficient and effective user interaction for long queries. My name is Girida Kumaran. I'm from the Department of Computer Science at the University of Massachusetts Amherst. I work at the Center for Intelligent Information Retrieval with Professor James Allen as my advisor. Most queries that are posed to search engines are usually 2 to 4 terms long, and we will refer to these as short queries. There's been a lot of research and development work towards handling these sort of queries, and they are generally handled well with considerable success. But in this talk, I'm going to talk about long queries, queries that are more than 4 terms long. And why are these long queries interesting? To start with, they have a natural language flavor to them. So these are the sort of queries that one human would ask another, or a knowledgeable person like a librarian, and so on. And they allow a user to express a complete information need instead of having to start with an information need and then coming up with a very concise representation of it and then searching with that concise representation. And from the perspective of a search engine, it provides context. So the user has provided a lot of information about their information need, and so the search engine can actually go through this really long query and try to figure out what exactly the person is asking for. But then, if you look at search engine logs, there aren't too many. The long queries are not a very large fraction of the total number of queries that users post to search engines. But then, for a moment, let us step back from this web search centric point of view and then look at other places where long queries definitely are issued as search queries. So here is a screenshot of the Microsoft Online help desk, and for example, the query in this case is, I'm unable to install anything on my computer, is there a fix? This sounds like a very reasonable query, but unfortunately, there are no documents that match this search. Let's go on to another example. How can I delete the history on my web search bar? This is not a concocted query. It's a query that was suggested by the autocomplete feature when I typed in the terms how and can. And this time, believing that there's a possibility that there is nothing in the Microsoft support content, I extended the search to include all of Microsoft.com. These are the results that I got, and from the screenshot, I believe that Live Search is now doing the search. The first result is copy, move, or delete documents from backward compatible documents, and so on. Clearly, it's not relevant to the original, to the information need of the person who issued the query. The second is delete a history item in Business Contact Manager for Outlook Express. Again, not relevant. And the third one, again, not relevant, restore or delete a previous version of an item or a file. So clearly, this query was meaningful, but the search engine doesn't handle it really well. I then went in and selected terms from this query. I tried a large number of combinations. It took me quite some time, say around 5 minutes, to figure that if I just use the terms delete, history, and web, I could get the information that I wanted. And this was, and the relevant page was right up at rank 1. So why should a user have to actually go in and reformulate the query? The question is, why couldn't the search engine have actually done it on its own? Why can't the search engine automatically analyze the query, find the important terms in the document, and then issue the query and get back these sort of results to the user? So this is the sort of basis for my talk and the reason why I think long queries are really important. But then the reality is handling long queries are tricky. This could to some extent be due to an artifact of the fact that most search engines prefer that users enter short queries because it's more easier to handle them in terms of going to the index and fetching the inverted list and so on. So this is a screenshot from the website of a search engine that encourages users to enter natural language queries in natural language. But it comes with some suggestions like don't use unnecessary words. So a query like ferries across Lake Michigan is preferable to what ferries can you take across Lake Michigan. Another suggestion, don't over specify your query. So a query like replacing spark plugs is preferable to something like replacing the spark plugs on my new Honda Civic. So you can see where they are going. They are trying to encourage users to enter shorter queries. In this talk, I hope to convince you all that to stop looking at long queries as a nuisance and instead start looking at it as an opportunity. And I will show that by using a combination of automatic and interactive techniques, we can obtain performance that is far better than what you can get with very competitive baselines. So before I go into the details, I will briefly describe the experimental environment and the results, and all the results that I'll report are pretty much experiments done in this environment, which is the Text Retrieval Conference, or TREC. So TREC queries have the structure that you see on the screen right now. They contain a title, a description, and a narrative, and each is of progressively increasing length. You can view the title as a short query. In this case, tobacco cigarette lawsuit. The description is a much longer expression of the same information need. So in this case, it is retrieve documents regarding US lawsuits against the tobacco industry for causing health problems and or death from cigarettes. The important thing to keep in mind here is that both the title and the description were issued or were created by the same person. In this case, it was an intelligence analyst. So just to reiterate, the title is used as a short query and the description is used as a surrogate for a long query. So let's analyze this example that I just this example query that I just gave you. You can clearly see that there is a need for analyzing this query and identifying what are the important terms in this query, the important terms or the important phrases or the important concepts. You can call it whatever you like. But to start with, terms like retrieve, documents, regarding are clearly noise, and only will seek to confuse the search engine further. And then we also need to identify the important concepts like US lawsuits, tobacco industry, health problems, cigarettes, and so on. But just identifying them is not enough. We also need to know how to weight them appropriately. So if your search engine just goes ahead and retrieves information about the tobacco industry, unfortunately that will not be relevant because it will not have information about US lawsuits and so on. So the challenges, as I look at it, is to remove the noise from the query and identify and appropriately weight the important terms and concepts in the query. I will now present the baseline performance or the baseline system that I used. So this query was issued against the TREC 2004 robust data set. These are basically a collection of newspaper articles and they number around 500,000. We use the query likelihood retrieval model, which if you look at the literature shows that it's pretty much a state-of-the-art baseline that can be used. And I will report results based on the NDCG at 15 metric. I will assume that almost everyone here is familiar with this metric and so won't go into the details. So if this query is run as is, and we used the INRI search engine, which is developed in collaboration between UMass and CMU. And if this query is issued as is using the query likelihood retrieval model, we get an NDCG at 15 of 0.357. I will now introduce the concept of query reduction. So, put simply, query reduction means dropping terms from the query and dropping the terms that are not useful in the original query. The idea is to identify the terms that are not useful and then just retain the core or the crux of the query and then use it as the new reformulated query against the search engine. Now, if some oracle told me what the answer was, it would be laws. I would just be retaining the terms lawsuits, tobacco, industry, problems, and death. And if I use that as my query using the same query likelihood retrieval model, my NDCG jumps 80% to 0.639. So clearly, there is great utility in this concept of query reduction. So you can also view it as assigning a weight of 0 to all the other terms in the query and assigning appropriate weights to the rest. Now, the query that I have out here that demonstrated this performance can be viewed as an upper bound. This would be the target. Suppose we were to develop an automatic system to identify the best queries, the best terms to retain. This would be the upper bound that we can obtain. And the way I obtained this upper bound was actually by considering all combination of terms from the original query. That's an exponential number. So for this small long query, if I did not do any stopping, if I didn't remove any stop words, then there are 500,000 combinations that I need to analyze. But, well, I went ahead just to see what happens if I use all the different combinations and what the impact was on the performance. So here is a snapshot of the top 5 subqueries. I'll refer to them as subqueries from now on, and the bottom 5 subqueries in terms of NDCG at 15. You can see that the top 5, if you manage to choose the best one, you can get an almost 80% improvement performance. But you can equally, there's an equal chance that you'll also make mistakes. So for example, if your technique, automatic technique to find the right terms picked cost, death, health, or cause, health, you would pretty much get an NDCG at 15 of 0.
So you're saying that in this case, if you drop the retrieve, you get lower values than what you're showing there for those middle, the third, fourth, and fifth? Because retrieve doesn't seem particularly relevant.
That's right. Retrieve doesn't seem particularly relevant.
When you looked at dropping those, they were actually slightly lower than 64, 63?
Yes, when they were retrieved, well, there seems to be some sort of a notion of an optimal size of a query. But then in this case, these are the best. But then if you remove the word retrieve, after some time, the actually performance goes down. And that's the interesting thing about the query reduction, which so you might get this reduced query that gets you better performance, but it might not be intuitive as to why it is really doing well. So why would retrieve be here and at the same time? But then there's a way to get around this problem, and I'll explain. I hope you'll understand in a couple of slides. So that was just for one query. So our training set consisted, this is not training in a machine learning sense. Our training set is the one that we use to analyze the subqueries. So we had a set of 249 queries, and we found, by doing this exhaustive search, we found the best subqueries for each of them. And then we just analyzed. To some extent, we did some failure analysis to see what was happening. And we found that these were the broad observations. Terms that the user believes are important in conveying the information need are missing. So in this case, there was the terms causing and health were missing at all. And obviously, the query was about causing health problems. And the noise terms are definitely missing. Retrieved documents regarding, clearly missing. And a few critical terms are enough: tobacco, industries, lawsuit, and deaths in this case. This also has to do with the fact that as to why are just 4 terms enough? It could also be an artifact of the way your retrieval model works. Maybe it can handle only maybe it is good at handling only words queries up to a certain length. And of course, there is this problem that Dennis just rightly pointed out. The shorter query ceases to be intuitive to the user. And the other interesting aspect is, if you remember, I told you that there are two portions to the trek query, the title and the description. And the title is a shorter version of the description. And it's created by the same person who came up with the description. So when we look at the best subquery and the title that was created by the same person, there is clearly a mismatch in a large number of cases. So you could claim that, oh, users, if given a long query, will figure out a way to find a shorter version of it, and why don't you use that? But then the reality is, users are not really that good in finding the best terms to use. And to some extent, that is because users have some notion of what is there in the collection. They are blind to the collection. They have some notion of information need, and they can describe it in some particular way. But the way the relevant information, the vocabulary that is used in the relevant for the relevant information in the collection can vary from the way the user describes it. So, so clearly there is great potential in doing query reduction. So, is there a way to automatically find these subqueries? And to give you a sense of how challenging the task is, for the example that I gave you, there are around 1,500 subqueries that are better than the baseline. And that's buried in a slew of bad ones. There are close to 500,000 combinations out there, and we need to identify this small set from that. And yes, the goal is to automatically identify a better subquery. It's not the best one. I'm not going to call it the better subquery, better than the baseline. So I'll now dive into a little technical detail as to how did we go about finding the best subquery. And to start with, we represented each subquery as a completely connected graph. Yes, all 500,000 of them, we created these completely connected graphs. And the vertices in this graph were basically the terms, and the edge weights were the mutual information between the vertices that are connected by the edge. We then went ahead and then found a maximum spanning tree on each of these graphs, and use the weight of the maximum spanning tree divided by the length of the tree as a score representative of the quality of the subquery. And we tried a number of metrics. These include finding the overall average of all the edge weights and so on. But then this decision to choose the maximum spanning tree was in part also motivated by the observation made by Van Rijsbergen in his 1979 book, that the maximum spanning tree incorporates the most significant of the dependencies between the variables. So to some extent, what we're trying to say is, okay, in this subquery, the terms are all very close to each other, or they basically, mutual information to some extent gives you an idea of how frequently the terms co-occur in the corpus. So if you have a very high maximum spanning tree weight, then it means that all these terms co-occur and therefore will support each other in retrieving information. And there are quite a few advantages to using this maximum spanning tree method. And the first is that we just need to construct the graph once. We can construct the graph with all the original query terms and then find maximum spanning trees on subsets of the graph. It's a symmetric metric, and it's very easy to compute. You don't need to do any retrieval at all. All you need to do is get co-occurrence statistics from your index, and that is not too expensive. And to some extent, I alluded to this in the last slide. It captures collection characteristics. So in our example, you may recall that the term cigarette was missing at all. Maybe in documents dealing with lawsuits, tobacco companies are referred to as tobacco companies and not cigarette companies. Whereas a human would have thought that, okay, maybe I should be using the term cigarettes. But then you can see that in that collection, relevant documents used the vocabulary in relevant documents included terms like lawsuits and tobacco, not lawsuits and cigarettes. So if we use this scoring technique and then look at the top 10, the performance of the top 10 ranked subqueries, we can see that right on top is cigarette and tobacco, which have very high mutual information, but unfortunately are missing key portions of the query. Therefore, it has a very low NDCG of just 0.06. As you go further down, if you look at the fourth one, so I've just increased the font size for the ones that did better than the baseline, there are quite a few of them that included terms like lawsuit and death and so on. And you can see that there are at least 3 of them that perform much better than, significantly better than the baseline. So you can get improvements from almost 24% to almost 29%. So that was for just one query, and now I'm averaging performance across a set of 249 queries that we use for testing this technique. The baseline was the long queries or the description portion of the trick queries, which had an average NDCG at 15 of 0.379. If we used the short query, that is the title, the one that was created by the same individual who created the description, we get there's an almost 8.7, there is an 8.7% improvement in performance. But if by some way we could always find the best subquery in the top 10, we will now refer to this as the interaction upper bound. So if we show this to a user and the user always picks the best one, then we can get a 30% improvement in performance over the baseline. And I also include the upper bound, which shows, well, how much farther we really can go. If an oracle gave us the best subquery for every query all the time, then we can get an NDCG at 15 of 0.626, and that's a 65% improvement in performance. And some additional analysis, which is quite interesting, is that only 20 or 1 in 4 of the best in top 10 matched the title that was created by the user. So, and at the same time, there was only a 16% exact match between title and the best subquery. So you can clearly see that there is scope for, to some extent, training users to either create the right query or providing them some way to help them reformulate their query and get a better representation or a better, shorter representation of the original query. So a quick recap on what I have presented until now is that, well, long queries are the reality, if not in web search. They are a reality in search verticals, they are a reality in help desk websites and so on. And they are clearly an opportunity, as you can see from all these improvements in performance that we can get. Query reduction helps, I've shown the numbers. And then we have a technique based on mutual information and finding maximum spanning trees to identify good reductions. And so now the question is, now we move on to finding a way to pick the best subquery from the top 10 that the automatic technique has found. And our answer to that is, let's ask the user. But before I go into details of a user study and so on, clearly a lot of you might have been thinking, so what's the use of this technique? If every time you're going to go through 500,000 combinations or 1,000,000 combinations, how can I even implement this in practice? The answer is we don't need to consider all combinations. So I'll draw your attention to this graph. On the x-axis is the query length of the long queries, and on the y-axis is the frequency with which queries have that particular length. The dotted line or the broken line is the distribution of query lengths of our baseline queries, which are the description queries. And you can see they range from, I guess, around 2 or 3 to almost 24 words in length. But then, if you plot the distribution of the sizes of the best subqueries, the ones that the Oracle gave you, saying that this is the best one, then you can see that most of them are between 2 and 4 terms in length, and they are never more than 10 terms in length, and so on. So this motivated a decision to stop this exploration of space to combinations of size at most 4. And you can see by doing this, we have not, again I have the numbers here, by doing this we have not lost out on any performance. So clearly we have gone from exponential sized analysis to polynomial sized analysis.
And what was the size of the corpus of data on which you derived this curve from?
Sorry?
What was the size of the data set based on which you derived those graphs?
This is just 249 queries, but that's what we have access to. So if we had weblogs, wow, that would be great. For some technical reasons, this slide hasn't appeared, but I'll just go on. So what was on that slide was, in the example that I showed you, you could see that there were only 4 of the options that were better than the baseline. That means I was potentially showing 6 to the user that were of no good at all. So would there be some way by which I can find a minimal set of options to show the user? Why always show 10? Why can't I show 2? Why can't I show 5? Then, so this is, I will now present a technique that we use to prune the set of options that we are going to show to the user. And the first one we'll refer to as set cover from now on. So consider a situation when we have 3 options to show to the user. So you have option 1. Now let us use option 1 to retrieve a set of 5 top ranked documents and keep them. Option 2 to retrieve another 5, and option 3 to retrieve another 5. Now, because of the fact that most of these options usually differ by a term or so, there's quite a chance that they will, the result sets that they retrieve will be overlapping in nature. So in this case, in this example, option 2 retrieves some documents that are retrieved by option 1 and some that were retrieved by option 3 as well. So what we do is we take the union of all these documents, and the union is represented here, and then try to find the minimal number of options we need to cover this set. And this is exactly the minimal set cover problem that we read in algorithm textbooks. It's unfortunately an NP-complete problem, but it has a greedy approximation solution to it, and a greedy approximation algorithm to it, and it provides, I think, a log approximation to the best solution possible. So that is one sort of pruning. The second sort of pruning, which you would understand better once I show you the actual interface, is that in the interface that we show to users, we in addition to just showing the options, we also show a snippet of text that option would retrieve if used as a query. So it is you can view it as providing the user some look ahead, saying that okay, if you select this option and if you wanted to use it, this is what you will retrieve, and that snippet is extracted from the top ranking document that option would retrieve. But then again, as I told you, sometimes these options differ by just a term or so, and so there's a chance that they might retrieve the same document and pick up the same snippet also, in which case it doesn't make sense. You're showing say 3 or 4 options all retrieving the same snippet, and there is no way the user can decide which one they require, which one they should be choosing. So in that case, as a first step, there is clearly a lot more we can do here. As a first step, we just pick one of the options at random and prune away the rest. Here are the results of doing it. So I have the baseline number as usual, and then the interaction upper bound. This is what the user can potentially achieve if they select the best option presented to them from the 10 that was displayed. So the average number of options in this case was 9.7. So there are some short queries that don't have 10 options to begin with. And if we do our set cover based pruning, it's not perfect, but then it doesn't prune exactly what we want. But then you can see that for a reduction of around 22% of the options that we show to users, we just take a 2% hit in the potential improvement in performance that we can. And after we do snippet based pruning, we can go down almost showing less one option on average, and we just go down 3% from the upper bound that we can get. So we've gone from showing the user an average of 10 options to around 6.5 options, but maintaining the same performance that we could potentially get. The second issue as far as efficiency is concerned that I want to address is, I'd like to draw your attention to this graph again. So on the x-axis are the queries. They are ordered by the potential improvement in NDCG at 15 we can obtain if we interact with the user. So our technique to find the subqueries are, they don't do well all the time. So you can see that in around 150 of the queries, these show some options that are better than the baseline, and so it makes sense to interact with the user for those queries. For close to almost say 75 of the queries, interaction doesn't have any utility. So why go and bother the user when interaction is of no use at all? So the question here is, can we decide beforehand, before we go and interact with the user, if we can, if there is any benefit in interacting with the user in the first place, and then bother them with this question? And the technique that we came up with was to analyze the set of options that we are going to present to the user. We looked at a whole set of predictive features to see if it correlates with the potential improvement in NDCG that we can get. So these graphs are not with respect to NDCG, they are with respect to average precision, but then there is a correlation of 0.8 between average precision and NDCG. So you can expect that these results will carry over to NDCG too. So the first predictive feature was original query length. So on the x-axis is the length of the original queries, and on the y-axis is the potential improvement in average precision that we can get for a query of a particular length. So you can see that there is a downward trend here. As the length of the queries increases, the potential for improvement through user interaction keeps decreasing. So to some extent, it's saying that as the original query keeps becoming longer and longer, the technique that we have used to identify these subqueries is getting confused. It is not able to do a good job. So there seems to be some sort of a threshold of around 20 terms beyond which it just doesn't make sense saying that, okay, now we need to figure an even better way to do this. The second predictive feature we used, which I'll refer to as spread of the options, just involves taking the scores for each of the options and then calculating the coefficient of variation. The coefficient of variation is nothing but the standard deviation of the scores divided by the average of the scores. And here you can see an upward trend. On the x-axis is the logarithm of the coefficient of variation, and again on the y-axis is the potential for improvement in average precision. And you can see an upward trend. As there is apparently more spread in the options, there is a greater chance that you can get an improvement in average precision. So we use these two features primarily, and just two features, so we could very easily threshold and figure out what are the values that we require to use, and then used it in a very interesting fashion. So, well, one obvious application is, okay, now you get a query, look at the top 10 options, and decide whether you want to interact or not. But then there is a more interesting application of this, in the sense that, let us imagine a situation where a user comes with a set of n queries to a search engine. So you could view this as a situation in which such situations can occur when you have like an exploratory search need. Suppose you want to vacation in Italy. So then you would have a couple of queries like Italy vacations, and then Italy resorts and prices and travel and so on and so forth. So what if a user came with a set of n queries and told the search engine, I am willing to interact. That's all the time I have. That's all I'm willing to do. I'm willing to interact with only, say, 30% of these queries. So it would be apt for the search engine to use this technique of determining the potential for interaction to go look at those n queries and find the 30% of those queries that will result in the most improvement in terms of mean average precision or NDCG and so on. So this graph is again for a set of test queries that we had, and the baseline performance was 0.235, again in terms of mean average precision. And through user interaction, the best performance, that is if you interacted for all the queries and then selected the best option, you can reach a score of around 0.268. Now what you see here are the three ways in which you can get to that improved performance. So if the first one, the lowest line, is random selection. So if the search engine looked at all the queries and said, okay, I'm going to pick 30% at random and 30% of the queries at random and interact with the user for those, then you would get the performance. So it would potentially go from 0.235 to around 0.245. But if the search engine was, say, an Oracle and knew which are the best queries it had to pick up in order to get the best performance through user interaction, then it would be the topmost line. So you can see that it starts off very high and then slowly tapers as the queries, as you include queries that don't have good potential for improvement through interaction. And if you use this technique based on thresholding with the query length and with looking at the coefficient of variation, you can get performance that follows pretty much the middle line out here. It's not as good as the upper bound here, but it is definitely much better than just randomly selecting queries. So a quick recap again. I have a feeling that the last few slides are a bit dense, but then long queries, you should view them as an opportunity. Query reduction works. We have a technique to rank subqueries, and we have done some simulated user studies that gives us upper bounds and what is the upper bounds on user interaction. And now I have addressed some issues on the efficiency, reduced it from exponential to polynomial analysis, and represented techniques to identify a reduced set of options to show to users, and a technique to determine interaction failure. I will now, in the next two slides, show the results of a user study that we ran. So this is the very simple interface that we used in our user study. We just displayed the long query and then showed the user the 10, or in this case, the 8 options. This is after the pruning, 8 options for this particular query. And then when the user clicked on each of these options, to the right, in the window to the right, would appear a snippet of text to help guide them in the decision as to which was the best subquery. And if the user did not like any of them, they could select none of the above and just go with the original query. So here is a snapshot of the results. We had 12 subjects for this user study. And this user study did not involve the selective user interaction aspect that I just talked about. So we could just pick user number 2 to see what sort of gains they got through interacting with the system. So the baseline, number subqueries selected. So all users were presented with 50 queries to work through, and number subqueries selected refers to the situations where the user actually went and selected an option and did not say none of the above. So for 16 queries in this case, user 2 decided did not like any of the options and decided to go with the original query. So for the 34 for which the user actually interacted with the system, the baseline NDCG was 0.314. And after user interaction, after the user went through each of the options, looked at the snippets and picked an option, they were able to improve the performance by 27.7%. That is, bring it up to an NDCG of 0.4. And upper bound. So upper bound here is what? So users clearly have made mistakes here, because in our example, there were 4 options better than the baseline. So the user selected one of them, and they could have done it in a suboptimal fashion. So they did not realize the true upper bound that could have been got through user interaction, and which was in this case almost twice that, which was 54% improvement. But then even this 27% improvement is no mean achievement. So I will now go on to, so all this time we have been talking about interactive query reduction, which is removing terms from the original query. But then I also showed you a graph in which interactive query reduction worked only for, say, around 60 to 65% of the queries that we considered. So, but then I will show that for some queries it is better to reduce the query, whereas for some queries it is better to expand them. And I will show how we can, and if we can selectively expand and reduce a query, then we can get an almost 50% improvement over the baseline compared to half what we got by using only IQR and only IQE. I'm sorry, this is an artifact of transferring from Office 2007 to 2003. So as you can see, if you expand a query, it looks like this. It's a mess. It's a lot of terms. There are automatic techniques to expand a query, and one of them is pseudo-relevance feedback due to Leverenko and Croft in a paper in 2001. You could typically expand your query with 100 terms, 200 terms, and of course all the terms that you add to the query are weighted in such a fashion that they don't take the entire mass of the query. So I'm still use the original long query that we have used an example for reduction, and you get, if you do automatic query expansion, you get additional terms like smoke, cigarette, tobacco, court, state, and so on and so forth. But then, being an automatic technique, it also makes a lot of mistakes. It draws in terms that are not related, that though they co-occur with your though they co-occur with your original query terms, they are not quite related to the original query. So if we can now take this set of terms suggested by your pseudo relevance feedback or any technique that you have to automatically suggest terms, and then try to find a good subset of terms from these, throwing away the noise that the automatic techniques have brought in, then we can obtain again a significant improvement in performance. So the claim here is that from this set of terms suggested by an automatic technique, we can find a smaller subset that delivers better performance. So, and in the case of, we'll refer to this question, to this technique as interactive query expansion as opposed to interactive query reduction. And all the techniques that I've described until now for interactive query reduction extend to interactive query relaxation too. So we can find all the different subsets, in this case again 2 to the n if you have n number of terms, and then you can again score each of those subsets using the maximum spanning tree based ranking that I described, and then we can again threshold on the set of subsets. We found that subsets of size more than 10 were pretty much useless, and we can also do the option pruning using the set cover based and the snippet based methods. And I have like a quick overview of the results that we could get by using interactive query expansion. If we use just the baseline query, which is again 0.379, sorry. If we used pseudo relevance feedback and did automatic expansion, we can improve performance, again this NDCG at 15, and get 0.397. But if we interacted with, so this is again the interaction upper bound, if we again found 10 options and then showed it to the user, and the user always selected the best option, we can get a 17% or a 80% improvement in performance over the baseline, and that's showing 10 options. But and if we go ahead and do set cover pruning, yes, we can expect a reduction in the upper bound performance through interaction. That's around 2%. So the performance goes to 0.437, but we have managed to remove almost 60% of the options. So we are now just showing 4 options to a user in exchange for a 2% or a 3% drop in performance. And if we continue with snippet based pruning, we can see that from 10 options we are now reducing to showing just 2 options per query, which is really significant. So here's the motivation for doing selective expansion and selective reduction. So on the x-axis is again the set of 250 queries that we have, and they are ordered by the difference in NDCG at 15 that you can obtain by either doing reduction or interactive query reduction or interactive query expansion. So as you can see, for close to almost 50% of the queries, reducing the query, that is removing the noise terms from the query, is better than expanding the query blindly. But for another 50%, it's better to actually just go ahead, say this means that the original query was pretty good, it is better to just go ahead and expand the query. So how do we do this? There are 2 ways in which we can do this. The first is, since we are using the same ranking technique for both sets of options, from the ones that we, for both sets of candidates, the ones for query reduction and the ones for query expansion, we can rank them together. But unfortunately, this did not carry on, this did not perform really well. The ranking showed a predilection for ranking the expansion subsets higher than the reduction ones, the reduction subqueries. So what we did was we merged, so we took 5 options from the top 5 options from interactive query reductions and 5 options from interactive query expansion, merged them to present the user with a set of 10 options. So you can see how successful this can be. So the baseline is again 0.379. If you do interactive query reduction, by showing the user 5 options, the best you can do is 18% better than the baseline. If you do interactive query expansion on the same set of queries, you can do 12.8% better than the baseline. If you take these 5 options from each of these techniques, merge them to do selective, interactive, relaxation, and expansion, that is showing 10 options, you can get a 37% improvement in performance. And that is showing an average of 9.9 options per query. Now you can go ahead and prune the set of options you show to the user using the set cover and the snippet based techniques, and you can see that by trading off just around 4% improvement in performance, you can get away with showing half the number of options. So what you would want to compare now is this value and these two values. By showing the same number of options as these two techniques, you can get a 34% improvement in performance compared to 18 and 12%. So in summary, what I want to convey through this talk is that long queries should be encouraged and not discouraged. Let us try to make the text boxes that users enter their queries into much longer, so that it encourages them to type in more information. And yes, we can leverage them pretty well. So these are all, currently I would view this as a foundation for further work. It would be great if we can come up with automatic techniques that can find the best subquery, and you never have to interact with the user and so on. And we can do efficient interaction, that is, we're talking about the background processes to support user interaction. We can do those in a very efficient fashion, and it's very effective. You can get close to 37% and 40% improvements in NDCG at 15. So, but then yes, it costs computation and user effort, but then it's probably worth the gain that we get. And I have also shown that there are ways in which we can make user interaction selective. That is, we can decide whether we want to interact with the user or not in response to a query. It can be minimal, so we can reduce the number of options that we show to users and still maintain performance, and it can be successful, and that is shown by the numbers that we get. So, and of course, all these results were shown on the same set of 249 queries that I've been referring to. We've done experiments on 3 different test collections with different sets of queries and different data sets, and found very similar trends in all the 3 collections too. So with this, I wrap up my talk on effective and efficient user interaction for long queries. In the remaining time, I would like to very briefly talk about another project that I'm doing that might be of interest to you. So I'm currently working on multimodal retrieval. So this is to some extent geared towards exploratory queries, in which, for example, here is global warming. It can be a very confusing query because, okay, what aspect of global warming is the user interested in? So my belief is that we should give, so you have all these different search spaces that this query can take you to. It can be global warming and effects on, and global warming and pollution, or global warming on climate, and effect of global warming on glaciers, and the relationship between global warming and Al Gore, and so on. So it's very difficult to clearly identify what the user is actually interested in. So this is not a concocted example. It's actually the output of a system that I'm just working on right now. So in response to a query like global warming, it makes use of 3 different modalities, or in this case actually search APIs. It uses the web search API, it uses the query suggestions API, and it uses the image search API. And by doing that, using the query suggestions API, it expands the query and then finds all the different variations that usually people use along with the query global warming, and then provides a preview of those results, and then clusters them, and then goes and uses image search to find an image that's representative of the cluster. So people can, if someone was actually interested in Al Gore and global warming, they can, instead of going through this entire result, they can just quickly go and see the image and say, okay, this is the cluster I'm interested in, and just dive into it. So with that, I conclude my talk. And for additional information on all the techniques that I described and the results, I would encourage you to go to my website and read my papers on user interaction. Thank you very much.
Just wondering if you could talk a little bit about this technique essentially is dropping terms out, it's reducing the terms, and described that as setting the weights to 0
Mhm.
on some of the terms. So what, other approaches to dealing with long queries don't set the weights to 0. But you didn't contrast your approach with setting the weights to 0 with, considering some of the terms at a lesser weight or treating some terms specially, like a question that starts with when might be looking for a date, for example. So I was wondering if you can talk a little bit more about potential advantages of setting them to 0 and potential disadvantages.
Mhm.
Could you repeat the question for me?
So the question is, the query reduction technique essentially drops terms by setting the weights to 0. But is that the right thing to do? Are there alternatives to doing it? And at the same time, can you treat certain terms in a more special fashion? Or can you analyze the query better, saying that in case there's a query like when did something occur, maybe you should be looking for particular types of information and so on. We did experiment with a number of ways of setting the term weights by saying that, okay, if I want to drop this query, then I've just reduced the weight by half and things like that. But the best option was to just set the weights to 0. And to some extent, I believe that is because of the particular retrieval model that we were using. So if you were to use a different retrieval model, maybe it can handle it better by reweighting it in a different fashion. So yes, the results that I present here are they are particular to the INRI search engine that we used.
Well, so related to that, I guess is the question implied there of related work. So for these particular data sets, have other people also gotten improvements over the baseline, and are you claiming yours is the best that you know of? How would you compare it to other people that work for this data set?
On this data set, people usually ignore the long queries and just report results on the title queries or the short ones. There isn't, as far as I know, any previous work that actually explores the notion of long queries and how better we can do, what are all the different techniques that we can use on these data sets.
And you mentioned, in addition to one you showed that had 200, almost 300 queries, you said at the end that there was 3 other data sets
Mhm.
that showed similar trends.
Yes.
These are also Trek data sets?
Yes, these are all Trek data sets.
Okay. And it begs the sort of the question of even on a handful of data sets, trying to extrapolate from this of how useful this may be in general, or if we had 1,000 or 10,000 queries, when will this asymptote? I'm wondering if you've done any other work. Is there any other work you can imagine doing or have done, even if you just had one data set, to try to understand whether this generalizes better to similar types of maybe larger data sets or anything else? What sort of, how do you get a sense of statistical significance here?
So the question was, if I got it right, was can you extend this kind of work to even much larger data sets?
And do you have any reason to have confidence that it would extend, or is it only going to, if you had 500 queries or 1,000 queries or different data sets, do you have any particular reasons to believe this is going to work or not?
I'm quite confident that this will work. I'm not sure about the web, because the web is clearly a different beast, because there's just so much information out there, and even if you type in any query, there's a chance that you might get something that's related to it. But then I would, with confidence, I would say that this technique will work in more limited domains. The example that I gave you was the Microsoft Help Desk, or in terms of vertical search. For example, if you have a health-based vertical search, usually people, if they type in information, they usually want to describe their symptoms and say what's happening to them and so on, and try to get relevant information. So that's a place where people will naturally enter really long queries. And the data that you have is also to some extent limited. You don't go out and search the web, but then you probably are retrieving from medical journals or articles on certain diseases and so on. So in those cases, I'm very confident that these techniques will definitely work.
And when we talked earlier about related work, even if there are other ones that have looked at long queries, you have been mentioning before that another sort of second baseline is just using the title as the query.
Mm-hmm.
And on the later slides at the end, you were still comparing to baseline of what people searched. I mean, did you compare it to the title as the query?
Yes, yes, I compared it with title also. So there are a large number of, I compared it to only automatic techniques, and there are quite a few of them, including, of course, pseudo-relevance feedback is an extremely strong baseline, and that's what people usually use. And I didn't show the numbers here, but in all my papers, you will also see results for pseudo-relevance feedback, and it does beat pseudo-relevance feedback. And the other very very strong baseline that I could think of is using dependence models. But then dependence models, so you can view this as a sort of a dependence model, because in a dependence model what you do is you just find all combinations of terms and then you put unordered windows on them, and then some of them might match and some of them might not. What we are doing here is, again, to some extent, by using mutual information, we are just trying to find which are the ones that you actually want to retain in the dependence model, which are the ones that will actually give you results. So, and of course, you cannot use dependence models for these long queries because there will be an exponential explosion and it will probably take you a day or two to get back results. And again, dependence models pretty much derives most of its strength from the fact that you do a dependence model and then you do pseudo relevance feedback and then you get a major boost in performance. So the actual component of improvement through dependence models is not is very small compared to what you get out of pseudo relevance feedback. So I hypothesize that even after you use dependence models, you won't be able to come to this level of performance. And as I said, clearly dependence models would not be applicable to these really long queries. As far as analyzing the query and doing, I guess, finding out what the actual target is and so on. So none of the queries that I have here really, none of the queries in my test set actually are the sort of queries you would find in QA. They generally are about finding documents and not finding specific pieces of information. So it won't be a fair comparison to compare both of them. And just to let you know, I also tried to use some NLP techniques to identify. So the notion was maybe only the noun phrases in the query are important, or maybe just the verbs are important. So I actually looked at the distribution of the parts of speech for all the long queries, believing that there may be some parts of speech that are not of any use at all and that we can just throw out immediately, and then the distribution of parts of speech for the best subqueries. And I found that there isn't much signal out there. There is clearly an overlap. So that's where it comes to the fact that the best subqueries are not really intuitive to the user and you don't know why they actually retrieve the document. And the best way to convince yourself that it is good is to look at the snippet of information and then
Actually leads into my next question, which was the problem here looks a lot like query suggestions, what search engines do right now, where you enter a query and they suggest ways to refine your query, but focusing query suggestions on taking long queries and suggesting shorter queries that perform better. But what you just said was that people don't know how to refine their queries if you try to look at the data.
Yeah, if
you're arguing that if you tried to look at the data of how people refine their long queries to short queries, you wouldn't actually get the optimal answer.
Yeah, so that's why, the title was created by the same person who created the description. And as a challenge, we had one graduate student actually going and saying, okay, I can do better. Now give me all the description queries and I will go ahead and create better ones. So here you have an experienced researcher in information retrieval trying to do it, and he couldn't come up with something that was as good as this. But that's not very scientific. Leave that. Okay, thank you.